Good morning, students. In the last class, we have discussed about some of the applications of opamp. That is how this opamp is going to behave as a voltage to current converter. So some applications we have discussed. So what are those applications? We have discussed about the comparators. In the last class, we have discussed about the comparators. So that is inverting comparator and non-inverting comparator. So inverting comparator means nothing but if you have given input signal to the inverting terminal of op amp, then that op amp is going to behave as a inverting comparator. So when we are going to apply the input to non-inverting terminal, that is input signal is applied to a non-inverting terminal, then it is going to behave as a non-inverting comparator. So we have discussed as the here coming to the inverting comparator operation. So here we are giving input to the input as a sinusoidal signal, and other input, that is non-inverting input, is grounded. So when we are making non-inverting input to be grounded, then this comparator, this op amp, here op amp is going to operate in a open loop configuration. So hence the op amp is the op amp input terminal, that is the signal which is applied at the inverting input terminal of the op amp is a sinusoidal signal. So when this sinusoidal voltage, signal voltage is going to be greater than the voltage at this non-inverting terminal, which is nothing but 0 volts, that is at ground potential. So when it crosses 0, then when the sinusoidal wave crosses 0, then the output is going to change its state. So the output is going to change its state. So initially, as it is a inverting comparator, the output is going to stay at minus Vsat. So when the sinusoidal input signal is at a positive excursion, that is during positive half cycle of the sinusoidal input signal, the output will be uh, at minus Vsat. You can observe that the output is inverted with respect to the input signal. So as here we are going to use op amp as an inverting comparator, so output will be also inverted. So this is the output we are going to obtain for inverting comparator. So coming to the non-inverting comparator, here in non-inverting comparator we are giving input to the non-inverting input signal to the non-inverting terminal of the uh, operational amplifier. So when the input is given to the non-inverting terminal of the operational amplifier, so as comparator function is nothing but the output must change whenever the input is greater than or less than, whenever the input is greater than or less than reference voltage. So with respect to that, if you are giving input to one of the input signal to one of the terminals of op amp, input terminals of op amp, the other input must be a reference voltage, nothing but. So for non-inverting comparator, we are giving the input signal to the non-inverting terminal and making that inverting input as grounded. So when a non-inverting input is grounded, so we can say that the reference voltage is nothing but ground potential, that is 0 volts. So whenever the input sinusoidal signal is going to cross the 0 volts, then the output is going to change its state. As here we have used this comparator as a non-inverting comparator, that means there will be the output will be not inverted. So that is how when we are applying a sinusoidal signal, that is a positive half cycle of a sinusoidal signal, the output will stay at plus V set only. It is not going to be inverted. And then when the sinusoidal signal is going to cross the zero volts, so at this particular point, the output is going to change its state. The output of the op amp is going to change its state from plus Vsat to minus Vsat. So this is how the output is going to change its state when there is a zero crossings. So hence this circuit is also called as, hence the circuit is also named as zero crossing detector. So the application of this comparator is, we can use this comparator in communication applications. Zero crossing detector, the zero crossing detector, op amp as a zero crossing detector. So this is used in frequency modulation also. Zero crossing detector is used in frequency modulation and demodulation. Uh, and coming to the next application, that is a logarithmic amplifier. So when we are discussing about this logarithmic amplifier is nothing but so the amplifier, the op amp, which is going to produce output which is proportional to the logarithmic value of input signal. So how this is going to produce? Just by introducing a diode D in a feedback path. So here op amp is going to act as an inverting amplifier, and we are giving the input to the inverting terminal of the op amp through a resistor R1, and based upon this resistor R1 and this diode that is applied at that is connected between that is connected as a feedback will provide will produce the output voltage which is nothing but which is proportional to the logarithmic value of input voltage. So here we are going to consider the nodal equation as well as diode current equation. When we are going to consider the diode current equation, so when it is forward bias, so the diode current equation will be like this. So from this nodal equation and diode current equation, we are going to obtain the relation, that is the relation between output and input. So here we can see the output and input. When we solve this equation by observing the circuit, we can observe that the output voltage is nothing but the output voltage is proportional to the logarithmic value of input voltage. So see here, in this equation, eta, Vt, and R1 and Is are constants, and Vi is only the variable. The input signal is going to vary. So logarithmic value of input is equal to output. That is, in output is proportional to the logarithmic value of the input, as other parameters present in this circuit is constants. So in this way, we are going to obtain we are going to produce op amp as a logarithmic amplifier. And coming to the another application, op amp as a anti-log amplifier. In logarithmic amplifier, as we have used op amp in logarithmic amplifier uh, in feedback path. Here in anti-logarithmic amplifier, we are using op amp, that is sorry, in the diode. We are using the diode in uh, at the input side, nothing but here you can see for an operational amplifier, the feedback resistor is provided as it is, and in the place of R1 resistor we are going to place a diode which is forward biased with the input signal, which is forward biased with respect to the input signal. So whenever the input signal is positive, the diode will be forward biased. So here nothing but we are going to place the diode at the input terminal between the input signal and the input terminal of op amp, that is inverting terminal of op amp, and we are going to place RF as a feedback resistor. And so that is nothing but here this operational amplifier is going to act as a anti-logarithmic amplifier. So by writing the nodal equations, And from the diode current equation, as the diode is a forward biased, from the diode current equation we are going to obtain the output voltage. Here you can see the output voltage, which is nothing but which is proportional to the e power of e to the power of vi, which is nothing but anti-logarithmic value of the input signal, as rf is and eta vt are constant values. So when these are constant values, then we can say that the output voltage produced by this circuit the the output voltage produced by this circuit will be proportional to the anti-logarithmic value of the input signal. So this is how we are going to obtain the anti-logarithmic value of the input signal. So these topics we have discussed in our last class. Now in this class we are going to discuss about rectifiers. Rectifier, what is a rectifier? As you know that, as you have studied in your electronic devices and circuits subject, a rectifier where mm, rectifier is a circuit which is going to convert the alternating current into the direct current, that is AC into DC. So the alternating current, why this is needed means, as the electronic equipments we are using in our house, home appliances, as a home appliances are going to work on DC voltages, are going to work on DC voltages, small DC voltages, nothing but whatever the components inside the mm, electronic devices is having in our home. So then they are going to work at a small DC voltages, but the supply voltage which is present in our homes is nothing but the AC voltage, and which is also having high voltage, which is also at a high voltages. So for obtaining the DC small voltages, we are using these rectifiers. Hence, before this rectification, we are using a transformer for step downing the voltage, and then we are going to connect this rectifier circuit. The rectifier circuit, which is going to convert the bidirectional current bidirectional current into unidirectional. Nothing but the bidirectional, that is as a AC is a bidirectional which is having both positive polarity as well as negative polarity. Here in this circuit, the in this rectifier is going to convert that bipolarized signal into the unipolar signal, that is the total current, it is going to make the total current into positive direction. So nothing but we can say another statement also, that is the circuit which is going to convert the alternating signal into pulsating DC, that is pulsating DC is nothing but a rectifier. So these rectifiers are classified into two types, that is one is a half wave rectifier and another one is a full wave rectifier. As you have studied in your EDC, half wave rectifier, which is constructed with the help of diode. The rectification done there with the help of the diode. Here, the rectifier, for this rectifier, we are going to use operational amplifier, and by using the operational amplifier, we are going to do the rectification. We are going to do the rectification. So here also we are going to observe the two types of rectifiers, that is half wave as well as full wave rectifier. So first we are going to discuss about this half wave rectifier. So when coming to this half wave rectifier, so we know that the half wave rectifier is a circuit that produces positive half cycles at the output. For that is a positive half cycle. Half-wave rectifier means in a sinusoidal signal we are having both positive voltages as well as a positive voltage level as well as a negative voltage level. So this half-wave rectifier is going to remove the negative voltage levels, and it is going to produce only the positive voltage levels at its output. That means it is going to produce only the positive positive signal. It is going to produce the positive signal at the output. As the sinusoidal signal is given as the input, it is going to produce the positive signal as the output. So now we are going to implement this half-wave rectifier using our operational amplifier. So when we are going to implement this half-wave rectifier using our operational amplifier, so here this is the circuit for implementing the half-wave rectifier using our operational amplifier. In this we are going to use an operational amplifier. So this is the operational amplifier in which the non-inverting terminal of op amp is grounded, and coming to the inverting input terminal, the inverting input terminal is connected to the input signal through a resistor R1, and here we are going to connect to two diodes. So one of the diode is connected between the output terminal of the op amp and the inverting input terminal of the op amp as a feedback, and another diode is connected at the output of this circuit and output of between the output of this circuit and output of this operational amplifier. So these two diodes are connected like this, and then a feedback resistor is connected to the output of this circuit and as well as input, that is inverting terminal of the operational amplifier. So now coming to the operation of this circuit, as we know that due to the virtual ground concept, as we know that due to the virtual ground concept, as the non-inverting terminal is grounded, so the voltage at this that is the voltage at this node is also the voltage at this node is also at ground potential, that is 0 volts. The voltage at this node is also ground potential. Whenever the input signal is applied, then what happens, the signal which is going to whenever the input signal is applied. So first we are going to discuss about for a positive half cycle of the sinusoidal input signal, the output of the op amp will be, so the output of the op amp will be negative. Hence the diode D1 will be forward biased. So see here. So for positive half cycle, the output of the op amp will be, so as we are going to produce the positive half cycle at the inverting input of the operational amplifier, as here the op amp is going to work as a inverting amplifier. Hence we have given input to the inverting input terminal. So then output will be a opposite polarity. Output will be of opposite polarity, and then when the output is opposite polarity, the diode here the output will be a negative, nothing but if we give a positive here, then the output will be at negative potential. So this negative potential is going to forward bias my diode D1. That is what we have discussed. So diode D1 will be forward biased, and when diode D is forward biased, so the output of the output voltage of the op amp will be at minus zero point 0.7 volts, that is diode cut-in voltage, nothing but so hence the voltage at this node is negative. This D2 diode will be reverse biased. D2 diode will be reverse biased. So negative will not switch on this D2 diode. So D2 diode will be reverse biased. Hence the output voltage of the circuit will be zero. Hence the output voltage of the circuit will be 0 volts. Therefore, there is no output of the half-wave rectifier for positive half cycle of a sinusoidal input. So for a positive half cycle, there will be no. So for positive half cycle, there will be no output present at the. Uh, there will be no output present. There will be no output present at the output of this circuit. So, and what is the operation of this circuit means here? So, coming to the operation again, I am going to explain here. So, when during the positive half cycle of the input signal, that is a positive half cycle of the sinusoidal signal, so the diode D1 will be forward biased. The diode D1 will be forward biased, and diode D2 will be reverse biased. So, diode, how this diode is forward biased? Hence, we have applied the input signal is positive to the inverting terminal. Then we can say that the output will be negative. the output will be a negative. So and that negative signal is going to forward bias this diode, and when this diode is forward biased, so that is the negative signal as we have obtained here, the negative signal through diode, the signal will be feedback to the input, fed back to the input again, and the output will be the output. Now we are going to take output at diode D2 terminal. So when we are going to observe this diode D2 operation, so as here the negative signal is obtained, so the diode D2 will be a reverse biased. So as the diode D2 is reverse biased, the output voltage will be zero. Hence, during positive off cycle, the output voltage will be zero. So the output voltage will be at zero potential, and there will be no output voltage during positive off cycle. And during negative half cycle, so for negative half cycle, what happens? For negative half cycle, you know that for negative input, so as it is inverting input, the output will be positive. The output will be positive. Whenever the output is positive, the D2 diode will be forward biased and D1 diode will be reverse biased. So the D2 diode, hence the D2 diode is forward biased. The output will be passed to the output will be, this diode is going to act as a closure switch, and here the output of operational amplifier is going to pass to the output of this circuit, and hence during negative half cycle we are going to obtain a positive signal here. The positive signal, see how we have obtained this positive signal means as so here you can observe here the op amp is going to act as a inverting amplifier. As we know that the gain of inverting amplifier is nothing but v naught by vi is equal to minus rf by r1. As we know that the gain of inverting amplifier is v naught by vi is equal to minus rf by r1. So this is the gain of this is the gain of our operational amplifier. Here op amp is going to perform as an inverting amplifier. So so when we bring this so when we bring that vi to this vi to right hand side, then the equation will be like this. So as here the vi is a negative, so minus of minus becomes positive. Hence the output voltage will be positive. Hence the output voltage will be positive. Listen once again. As during negative half cycle, during negative half cycle, that means the input voltage is negative. So negative minus into minus will becomes positive during negative half cycle. The output produced by this circuit will be positive. The output produced by this circuit will be positive. So this is how we are going to the circuit is going to produce mm, the circuit is going to produce only the positive, mm, only the positive half cycles, only the positive half cycles, and this is how it is going to produce a half wave. This is how our op amp is going to produce act as a half wave rectifier. This is how our operational amplifier is going to act as a half wave rectifier. This is the operation of the op amp as a half wave rectifier. And next we are going to discuss about these are the waveforms. As we have given a sinusoidal signal as an input, then it is going to produce a pulsating DC signal. So here you can see the pulsating DC signal. So during positive half cycle it is 0 volts, and during negative half cycle we are going to get the positive pulses like this. So next coming to full wave rectifier. So next we are going to discuss about this full wave rectifier. So for this full wave rectifier, so uh, we have taken two operational amplifiers. So in which one of the op amp is going to, okay, one of the op amp is going to produce is going to work as an inverting amplifier, and another op amp is going to change its function. So one of the op amp is going to work as an inverting amplifier, is going to work as an inverting amplifier, and another op amp is going to change its function according to the operation of the first op amp. That means the second op amp is going to act as a inverting amplifier during inverting amplifier, and as well as it is going to operate as a non-inverting amplifier also. So during the operation, during the operation of this process, that is operation of this circuit, explaining the operation of this circuit, we are going to see there how this circuit is going to work. So here you can see the first op amp is a inverting amplifier. The first op amp here is going to act as inverting amplifier, as non-inverting terminal of the first op amp is grounded. So and input is given to the inverting input terminal of the op amp. The output is connected to the two diodes. So see here, one of the diode, that means anode terminal of the diode is connected to the output. Here another diode cathode terminal is connected to the output. That means whenever the output of this op amp is negative, D1 is going to conduct. Whenever the op amp output is positive, D2 is going to conduct. This you have to keep in mind. So whenever the output of first operational amplifier is positive, then D2 is going to be forward biased. Whenever the first operational amplifier output is negative, then D1 is going to be forward biased. So in this way, so it is going to do its functioning. And coming to this op amp, so whenever there is no, whenever D2 is reverse biased, then we can say that the output as this you can see here, as this is connected to this node through R3. So we can say that there will be this will be at a ground potential approximately equal to the ground potential. So hence at that time the op amp, this second op amp is going to work as a non-inverting amplifier. And when this diode is not functioning, this diode is off, then this terminal will be grounded, this terminal will be grounded, and this second operational amplifier is going to work as a non-inverting amplifier. So with this we are going to see the we are going to observe the output, how it is going to produce the output of the output of this op amp we are going to see now. So, so what happens for positive half cycle of the sinusoidal input, the output of the first op amp will be negative. So, hence the diodes D1, D2 will be D1 and D2 will be forward bias and reverse bias respectively. So, D1 will be forward biased and D2 will be reverse biased. So, coming to the operation of the circuit, when input is a positive half cycle, so what happens, the output will be a negative. So when the output is negative, D1 will be forward bias, as we have discussed that, as we have said that, as I have said that, the whenever the output of the first op amp is negative, then this D1 will be forward bias, and D2 will be alternatively, the D2 will be a reverse bias. Simultaneously the D2 will be a reverse bias. And what happens when D1 is forward biased? So the current, when D1 is forward biased, then the output voltage of the first op amp will be, so V01 is equal to, so here the first op amp is going to act as a inverting amplifier. So we have written the equation for gain of inverting amplifier, that is we are assuming that the output of first op amp as V01, and V01 is equal to minus R2 by R1 into Vi. So why we have written minus R2 by R1? Because the feedback resistor for this operational amplifier is nothing but R2, and the series resistor is nothing but R1. So we know that the gain, which is equal to minus RF by R1. So in the place of RF, here we are having R2, and in the place of R1 we are having R1. So with that we are going to write the equation as V01 is equal to minus R2 by R1 into Vi. So when we observe, the output of the first op amp is connected to a resistor R4. Hmm? So output of the op amp is connected to a resistor R4 here, as this is forward biased. Whenever this is forward biased, then the output is connected to a R4. So R4, which is connected to the inverting terminal of the second op amp, nothing but here R4 is connected to the inverting terminal of second op amp. So here R4 is going to act as a series resistance of a second op amp, series input resistance of a second operational amplifier. So second operational amplifier. So mm, the voltage present at the non-inverting terminal of second op amp is 0 volts. So the second op amp with R4 and R5 is going to act as inverting amplifier. So this, as diode D2 is reverse biased, there will be no voltage at this node. And as we know that due to virtual ground concept, the as this terminal is grounded, we can say that the voltage at this node is also zero. Hence, we can say that the non-inverting terminal of second op amp is also grounded. So hence this second op amp is going to act as a non-inverting amplifier. Is going to act as a non-inverting amplifier with the input resistor as R4 and feedback resistor as R5 and feedback resistor as R5. Here the input is applied through diode D1, and we know that the output of this op amp is a negative. So negative is applied to that is the negative signal which is applied to the inverting terminal of op amp, then the output will be inverted. The output will be inverted. That is, as negative is applied as the input of this inverting amplifier, then the output will be positive. So in this way, the output of this operational amplifier will be positive during positive half cycle. The output of this full wave rectifier is positive half cycle only. We are getting only positive excursion. So we are making nothing but we are making bidirectional current into unidirectional current. This is the operation during positive half cycle of our sinusoidal input signal. Positive half cycle of our sinusoidal input signal. And coming to the negative half cycle, so what happens during negative half cycle? So if you observe the output of the second op amp, so we know that the output of the second op amp V naught is equal to nothing but it is also going to act as a non-inverting amplifier. So V naught is equal to minus of R5 divided by R4 into V naught 1, because here the feedback resistor is R5 and input series resistor is R4. So R5 by R4 into input is nothing but V naught 1, which is the output of first operational amplifier. So we are writing V naught 1, and we are going to calculate the total output. If we are going to calculate the total output, nothing but V naught is equal to, so in the place of V naught 1, we are going to substitute, as we have derived the equation for the V naught 1 here. So we are going to substitute this value here in this equation. So we are going to get this equation: V naught is equal to minus R5 by R4 into minus 1 R2 by R1 into Vi. So V naught is equal to, finally we are going to get, as minus into minus will become plus. So here we can see the output will be a positive voltage. The output will be a positive voltage, and the amplification is going to depend upon this resistors R2, R5, R1, and R4. So if all the resistance values are equal, if all the resistance values are equal, and then we can say that the output is equal to input. The output is equal to input. In this way, it is going to produce the positive half cycle of the positive half cycle as its output during the positive half cycle of the input signal. So during the positive half cycle, so we are going to get the positive half cycle as it is. There will be no change with this circuit. So, and coming to the operation during negative half cycle. So during negative half cycle, what happens to this circuit? So when negative half cycle is applied as the input to this first operational amplifier, so what happens? So when negative half cycle is given as the input, so then what happens to this circuit? So here, as the op amp is going to act as a non-inverting amplifier, so the output will be, input is negative, then output will be positive. So when the output is positive, D1 is reverse biased and D2 will be forward biased. So the current now going to flow in this direction. So and this signal will be applied to the our operational amplifier, that is non-inverting input of second op amp, non-inverting input of second op amp. Then This second op amp is going to now this second op amp is going to act as a non-inverting amplifier. So how this is going to act as a non-inverting amplifier, we will see. So as this diode is forward biased and as this diode is reverse biased, we can say that the voltage at this node will be there is no current flow in this direction. The voltage at this node will be zero. So as you have seen that, as we have observed that this is due to virtual ground concept, the voltage at this node is zero, then the voltage at this node is also zero. If you assume R2 is as very low value, then the voltage at this node is also at zero potential. So hence this terminal is grounded. And the circuit of the second operational amplifier, if you consider this circuit is going to act as a non-inverting amplifier. So when as the negative signal is given, the voltage here, the current produced by this op amp is positive, and this will be applied to the uh, non-inverting input of second op amp. So this op amp is going to act as a non-inverting amplifier, and hence if you write the equation here for second for negative half cycle, so v naught 1 here, the first op amp is going to act as a inverting amplifier. So v naught 1 is equal to minus r3 by r1 into vi. That will There will be no change in this equation. But coming to the second op amp here, second op amp is going to act as a non-inverting amplifier, and hence the output of the second op amp is equal to, as we know that the output of non-inverting, that is the gain of non-inverting amplifier will be v naught by vi is equal to 1 plus rf by r1. So in the place of feedback resistor we are having r5 resistor, and in the place of series resistor we are having r4 resistor. So 1 plus r5 by r4 into v naught 1 is nothing but the output of the first operational amplifier. So in the place of v naught 1 we are going to replace this equation. So what happens here, you can see. So the output is equal to minus of R3 by R1 into 1 plus R5 by R4 into Vi. So as the input signal is negative, and if R1 is equal to 2R3 is equal to R4 is equal to R5 is equal to R, then this all this factor, that is r3 by r1 1 plus r5 by r4 is equal to 1. Then as input is negative, then minus of this minus will become positive, so output will be a positive. So the output of this full wave rectifier is a positive during negative half cycle. So here you can see the positive current is flowing, and we can see the output voltage obtained at the output of second op amp is also a positive. So in this way, in the both cycles, that is for the input signal having half positive half cycle as well as a negative half cycle, so the op amp is going to produce the full wave rectifier is going to produce the both cycles, that is in unidirectional. The current flowing through the op amp is unidirectional. Output of this circuit will be in unidirectional. So in this way, it is going to produce op amp output for a full wave rectifier. This is the signal output signal produced by the full wave rectifier. So in this class, we have discussed about rectifier circuits mainly. So rectifier circuits are of two types. They are half wave rectifier as well as full wave rectifier. Here we are going to implement the rectifiers using the operational amplifier. Here we have implemented the rectifiers using our operational amplifier. So when we are going to use this op amp for rectification purpose, there here we have discussed about two rectifiers, that is one is a half wave rectifier as well as full wave rectifier. So half wave rectifier is going to produce the half cycles during negative half cycle of the input signal, and full wave rectifier is going to produce the full cycle. That full wave rectification is possible by this op amp, by this operational amplifier. Next, we are going to discuss about the square wave generator and the triangle wave generator. The square wave generator as well as the triangle wave, the square wave generator as well as the triangle wave generator. So what happens? So coming to the next application, that is a op amp as a square wave generator, and this circuit is also named as a stable multivibrator. So as you have studied in your PDC subject, pulse and digital circuits, so there you are going to study about the multivibrators, which is nothing but there are three types of multivibrators: bistable multivibrator, a stable multivibrator, and monostable multivibrator. So here, as it is a square wave generator, we can say this circuit is also called as a stable multivibrator. So which is nothing but which is also called as free running oscillator, because this circuit is going to produce a square wave, that is a non-sinusoidal signal, that is a square wave as its output. And here mainly you can see this op amp is going to work as a comparator, nothing but op amp is going to work as a comparator, which is going to compare the input signal with respect to the reference signal. So here there is no, as this is a generator, there is no input signal and there is no reference signal which we have given. So we have given only the supply voltages, and we have connected a circuit such that you can see the op- output of the op amp, that is the feedback is provided, the negative feedback is provided with the R1 resistor, and the positive feedback is provided with the R2 resistor. So hence with this feedback, so here there will be feedback. The feedback is provided here. So the negative feedback is provided by this the negative feedback is provided by this R1 resistor, and positive feedback is provided by R2 resistor, whereas here this node is grounded through R3 resistor, and that means the compensation is provided. So here Vp is going to act as a reference voltage, and Vn is going to act as the input voltage. And hence when we switch on the supply, what happens initially, if we assume that there is no charge across the capacitor, into capacitor లో అసలు charge లేదనుకున్నాం, there is no charge across the capacitor, and then due to offset voltage, due to some offset voltage at the non-inverting terminal of the op amp, the output of the op amp will be the output of the op amp will be minus Vsat. The output of the op amp will be at plus Vsat. So what happens? The Due to the offset voltage, the output of the op amp will be at plus Vsat. So plus Vsat దగ్గర ఉంటుందన్నమాట. Then this plus Vsat is going to be applied as the input to the operational amplifier, that is to the inverting terminal of the op amp through a capacitor. So now the plus Vsat is going to charge this capacitor. So now the capacitor is going to charge the value to the plus Vsat. So what happens to this capacitor value? As we know that these two nodes are at same potential, that is Vp and Vn must be at same potential. So as the capacitor is going to charge to plus Vsat, the capacitor now is going to charge through this resistor R1. So when this capacitor is going to charge to a resistor R1, when this capacitor is going to charge to a resistance through a resistor R1, so this capacitor charge is going to move. This capacitor is going to charge towards plus Vsat. So as the voltage across the capacitor is going on increasing and increasing and increasing, so whenever it crosses the voltage, that is the Vp, the reference voltage, so then the output is going to change its state. So now the output, initially the output is at plus Vsat. So whenever the capacitor voltage is going to cross Vp, that is whenever the voltage across the capacitor is greater than this Vp, whenever the voltage across the capacitor is going greater than this Vp, then the output of this comparator is going to change its state from plus Vsat to minus Vsat. So the output of this comparator is going to change from plus Vsat to minus Vsat. So the output is at now the output is at minus Vsat. Now the capacitor is going to discharge. Now the capacitor is going to discharge. through the resistor R1. And what happens now? The capacitor is going to discharge towards minus Vsat. The capacitor is going to discharge towards minus Vsat. And when again the voltage across the capacitor, when the voltage across the capacitor is less than the voltage at this node, that is Vp, again the op amp is going to change its state from minus Vsat to plus Vsat. So in this way, it is going to produce a signal which is going to fluctuate, which is going to change between plus Vsat and minus Vsat. So here you can see what happens generally. So the capacitor is going to charge like this. So whenever the capacitor is going to charge like this, the capacitor is going to charge and going to charge towards hmm, plus Vsat. The capacitor is going to charge towards plus Vsat, and whenever this capacitor is going to um, charge up to Vp, whenever this capacitor crosses this Vp, then capacitor charge crosses this Vp, the output is going to change its state. The output is going to change its state from plus Vsat to minus Vsat, and again the capacitor is going to discharge. The capacitor is going to discharge in this way. So whenever the capacitor voltage is less than this Vp, again um, the output is going to change its state. If we observe this, if you observe that charging and discharging of this capacitance value, then we are going to obtain the square wave. So based upon this capacitance charging and discharging, and this capacitance value and resistance value, it is going to produce a square wave. So if we change the value of this capacitor and resistor, we can change the time period of this square wave. Time period of this square wave. This time period of this square wave is going to depend upon this resistor and capacitor value. So this is how my op amp is going to produce a square wave. So next application is a triangle wave. So when my op amp is going to, as we know that we have studied that op amp is going to produce a square wave. So when this square wave is applied to an integrator circuit, and the square wave is applied to an integrator circuit, then nothing but the square wave is going to integrate. It is going to be integrated, and it is going to change its that is, it is going to change its shape such that the output obtained from the integrator is nothing but a triangle wave. The integrator is nothing but a triangle wave. The square wave generator output is connected to an integrator, then we are going to obtain a triangle wave. So here, this is a square wave generated, what we have discussed now, which is going to generate a square wave, and then we have applied that output of the square wave to an integrator circuit in which Ri is the resistor and Ci is the feedback capacitor. So by this integrator circuit, we are going to the output is going to be produced a triangle wave. So the waveform will be, so this is going to produce a square wave. Sorry, this is going to produce a square wave. So this is the square wave produced by our first operational amplifier, and then the output of this the output of this will be a triangle wave. So it is going to generate a triangle wave. The capacitor is going to charge like this, and again during negative half cycle, the capacitor is going to discharge, and during positive half cycle, again uh, the capacitor is going to charge. So in this way, in this manner, it is going to produce a square wave. So here you can see, if I draw, if I draw, so here you can see, if I draw a triangle wave like this, triangle wave will be, sorry, so triangle wave will be like this. So like this. So like this, the output of the integrator will be like this. So as the square wave is given as output of this integrator, now as the square wave is given as output of this integrator, so the integrator integrates over the time period t, and we are going to, it is going to produce a triangle wave like this. So based upon this R and C values, we will obtain a triangle wave. So based R and, if you adjust R and C values, the triangle wave slope can be managed. The slope can be adjusted. So in this way, we are going to produce we are going to generate a square wave as well as a triangle wave. So where this is applicable in our laboratory, you know that we have function generators. So in that function generator, so for generation of the square wave and for generation of the triangle wave, we can use this op-amp circuit. We can use this op-amp circuit simply for generating a square wave as well as for generating a triangle wave. So thank you. So in this class, we have discussed about the op-amp rectifiers and as well as square wave generator and triangle wave generator. Thank you, students.